Hello guys, in this video we are going to learn about Tarjan's algorithm. Tarjan algorithm is used to find SCC in a graph. If you want to learn about a strongly connected component in details, please check my previous video in which I have explained what are SCCs and what are their applications along with the Kossaraju's algorithm. Kossaraju's algorithm is also an algorithm which is used to find SCC in a graph, and the time complexity it's big O of V plus E, where V is the number of vertices and E is number of edges in a graph. The problem with this algorithm is it takes three passes. So it scans the graph three times, and each time it takes V plus E time. Hence, the complexity here is 3 into V plus E. As we remove constants from a complexity, so the complexity is big O of V plus E. So Tarjan algorithm is an improvement on it. It just scans the graph in a single time, and it gives us all the SCCs present in a graph. So let's look into the Tarjan's algorithm by using a dry run first. Then we will come back to this algorithm and everything. So let's go down. So Tarjan algorithm uses a few arrays. Let's see what arrays it used. So one array it uses disk array. So disk array is an array which it uses to store the discovery time of a node. So it basically uses DFS only to find the SCCs. But when a node is discovered in the DFS process, we store that time in the discovery array, or it's called ID array, whatever you can name it. But it stores the discovery time of a node in an array. Then there is an array called low. Low basically represents what smallest node can be reached from a particular node. For example, let's say we start from 1, then we go to 2, then go to 7. So from 7 we can reach 1, right? So whatever 1 is smallest than 7, because 1 came into the DFS before 7, right? So whatever smallest, or whatever the most back edge can be found in a graph. So from 7, the smallest parent that we can reach is 1, right? We can through this edge. So low array represents that part of the graph. And on stack, it just mentions, it sets the boolean array. It just tells you whether a node is present on a stack or not, and we have a stack as well. So let's first take a look at the dry run, then we will come back to this algorithm. Okay, so initially the time will be 0 because when we start DFS, the time we will taking as 0. So discovery and low are initialized to 0, and on stack array is initialized to false because none of the element is on the stack yet. Stack is empty. Now when we start our DFS, we increase the time by 1, and as we are starting our DFS using this one node, we will mention that time into the discovery as well as low, because this node is getting discovered for the first time, right? There is no other processing that is being continued. So initially we will just mention the time in both discovery as well as in the low array of this node, and we will just push this node onto the stack and just make the stack variable 2 on this array as well. Now from 1 we move to 2. So I've just mentioned I've just shown the active path using green colors. So this will just tell you that this path is still active. So now we increase the time again, and now for the node 2 we set the discovery time as well as the value of low as 2, and we push it onto the stack as well and make the on stack variable 2 for it as well. Let's move forward. Now it will go to 3. So on 3 we'll increase the time again, and we store it in the discovery as well as the low value of node 3, and we push it on the stack, and we just make the variable of on stack 3 true. Now after 3 there is nowhere else to go, right? Because we cannot go back in DFS before processing a node, right? So 3 is not going to any other node, so hence the processing of 3 is complete. So when the processing of a node is complete, then we just check if the discovery of a node is equal to the low value of the node. If that is the case, we just pop everything from the stack, and we form an SCC with all the elements that are coming out of the stack. So we as we see, the processing of the 3 is complete, right? So we will pop elements from the stack until we get the node 3, and whatever elements will come out of the node, we will just create a SCC from them. So as in our stack, as we see, we have only 3 elements and 3 is on the top, right? So we have only one element and popping out of stack until the 3 comes, right, which is 3 itself. So we will just create a SCC using 3 only. Now after the 3 processing is complete and the stack is popped out, you will see something like this. So 3 is popped out of the stack and everything else is still same, and we have made the on stack value for the 3 false because it's not in the stack anymore, and we have formed a single SCC using a single node called 3. Now we go back to 2, right? So once when we go back to 2, so we came back to 2 after a child node is completely processed, right, before moving to 7. Now we will just look what we will just update the low value of 2 based on the discovery and low value of 3. So as the 3 is a child of the node 2 and we have come back to node 2 after processing is completed for node 3, we will just check if the low value of 2 is less than or equal to the low value of 3, and we will just store the minimum value of both of them. So it will look something like this. Low value of 2 will be updated, low value of 2 will be minimum value of low of 2 and low of 3. So we see low value of 3 is 3 and low value of 2 is 2, hence the minimum value is 2, right? So no change will happen, it will still remain 2 because we will take the minimum value from both these values. So there is no change happening here, and we will move to 7 because we in DFS, once a child processing is complete, we move to another child, right? Like it's like we keep on moving forward, right? If you want, you can watch a video on DFS to better understand it. But after completing the after completing the processing of node 3, we move to node 7. Hence we increase time again because we are discovering a new node, and we store it in the value of 7. So in the 7 we store it the discovery as well as low value of 7 as 4, and we push it on the stack and make the true variable true on the on stack array. Now from 7 we have 2 paths, right? We can either go to it or we can either go back to 1, which is like already visited, right? Let's try this path first. So from 7 we can go to 1, but 1 is already visited, right? We can tell that by checking the on stack array. So if the on stack array for 1 is true, like 1 is already in the stack and already in the processing, right? It's already visited, so we don't go back there. So we just know by this edge that from 7 we can reach a previously visited node that is already be visited before in time, right? So we find out that. So for 7 we will just update the low value of 7 by the low value of by the minimum value of low 7 and discovery of 1. So we will just say here that when the 7 was discovered and whatever parent 7 can reach, whatever the minimum value is there, we will just store it in the low value of 7. So low array basically tells you what smallest parent a node can reach. So here a 7 was discovered after 1, right? And 1 has a smaller discovery time and 7 has a higher discovery time. So we will just compare the minimum of low of 7 and discovery of 1, because it could be possible 7 can reach a let's say if the graph was more complex, like this is a fairly simple graph. Let's say there was a node which is before 1 as well, like 0 node, and 7 has an edge to that 0 node as well, so it can reach 0, right? So for each node that 7 can reach and that is already visited, we will just store the low values of all that minimum low value of all these nodes. So let's say 7 can reach 1, then if there would have been a node 0 before 1 and 7 has an edge to that 0 as well, then we will just store the minimum of all 3 low values. So one by one we just calculate in a iterative manner. So we will just say low value of 7 is equal to minimum of low of 7 and discovery of 1. So whatever smallest node 7 can reach, it will just it will be stored as a value in the low of 7. So as we see, low of 7 is 1, sorry, not here, as we see, low of 7 is 4, and the discovery of 1 is 1 in this array, right? So minimum value from 1 and 4 is 1, right? So we'll store 1 in the low of 7. So updated value will look like this. Let's move down. Now the processing of this path is complete, so we move back to another element. So from 7 we can reach 8, right? So when we move to 8, as we are discovering a new node, we increase the time by 5 and store the 5 as a value in discovery as well as low of node 8. So it's updated here. Now as 8 is a leaf node, so because leaf node, it's not a tree, but from 8 we cannot reach, we cannot go anywhere else, so the processing here is complete. It has no children, right? So we will just do the same thing. We will just check if the discovery of 8 is equal to low of 8. If so, then we pop out all the elements from the stack until we get the 8, and we create a SCC from them. So our stack is looking something like this. So we will just pop all elements from the stack until we get 8. So as you can see, 8 is on the top again. So we will just pop out a single element, which is 8 itself, and we will make it false on the unstack array. We will pop it out the stack and we will create a SCC using 8 as 8 only. Now after the processing is complete, we move back to parent, right, which is 7. Here we will again do the same thing. We will just check if low of 7, we'll just again update the low value of 7 using this operation, which is minimum of low of 7 and low of 8. So this operation we do because we know from 7 the smallest node we can reach is 1, right? But there could be another scenario, right? For example, let's say there was a node 0 on top of 1 and we started from 0, and 7 has edge back to 1. Let's say 8 would have edge back to 0, something like this. 8 might have a edge back to 0. Then from 7 we can reach 1, but from 7 if we go through it we can reach 0 as well, right? So to cover this scenario we do this kind of operation. So we just check whatever smallest parent we can reach from this node, and whatever smallest parent this child could reach, because if child can reach a smaller parent than the 7, then 7 can also reach it, right, by using this path. So we do this operation to figure that to cover that scenario actually. So we compare both the low values of 7 and 8 and we update it with the minimum value. So low of 7 and low of 8, let's see what it is. So 7th low is 1 and the low of 8 is 5. Minimum is 1, so there is no change. It will still be 1 for 7. Now let's move back. Now after we have processed all the children of 7, which is 1 and 8, so 1 we can go because it's already in discovery mode. 8 is done and we cannot go anywhere else from 7. 7 is also complete, right? So we again do the same thing. We check if discovery of 7 is equal to low of 7 or not. If so, we will pop the elements of the stack, otherwise no. So we check the discovery of 7 is 4 and the low of 7 is 1, which is not the same, right? So we'll just leave it as it is. We will not pop anything out of the stack and we'll move forward. Now after 7 we just go back to 2 again. So now 2 is also complete because all the children of 2 are processed, right? Same process will happen here as well. So discovery of 2 is not equal to low of 2 as well. So discovery of 2 is 2 and the low value is 1. Sorry, I missed a step, I guess. Yeah, so after 7 is complete, when we move back to 2, right, we again check the same thing for 2. When we move back to 2, because we have come back after a child is fully processed, right, we again do the same thing. Minimum of low 2, minimum of low 2 and low 7 is stored in the low of value of 2 to do the same thing, right? So low of 2 is where it is, low of 2 is 2 and low of 7 is 1, and the minimum value of these two is 1, right? So we update the low of 2 as 1, which is like this. So update the value of low 2 as 1 as well. So here we covered that scenario, right? Because from 2 we cannot directly reach 1, right? But if we follow this path we can reach 1 through 7, right? So to cover this scenario we perform this. So it tells us that from 2 also a previous parent can be reachable. So after this the node 2 is also completely processed and we again check if the discovery of 2 is equal to low 2. If so, we pop out of the stack, otherwise we don't do anything. And we see here discovery of 2 and low of 2 are not same, so we move forward. Now we go to 1 again, because after 2 is complete, we go to 1 again and we do the same thing, because we are coming after processing a child of 1, right? So here again the low of 2 and low of 1 are like same, so there will be no change in 1 and value will be same, and we move to 4. Since we are discovering a new node, we increase the time and store 6 as the value in discovery and low of node 4. We push it on the stack and make the stack variable true. Now from 4 we can either go to 5 or 6. I'm just going to 5 first. Increase the time, put the value 7 as in the discovery and low of node 5, which I put here. Push it onto the stack and make the stack variable 2. Now from 5 we cannot go anywhere else, right? So we'll just check. So processing is complete for 5, so we'll just check if the discovery and low are same for 5. If so, we'll just pop it out of the stack. So we see the discovery and low value of 5 are same. So here, as you can see, the discovery and low are both 7, right? So values are same for discovery as well as the low of 5. So we will just pop out elements from the stack again until we get 5 and form an SCC from them. So on the stack, 5 was on the top, so we just pop out 5 and create SCC using 5. Now after processing this, we go back to parent and we do the same operation. Minimum of low 4 is equal to minimum of low 4 and low 5. And as we see, low of 5 is 7 and low of 4 is 6. So there will be no change happening, like it will still remain same. So it will still remain same, and we move to 6. Then next child of 4, which is 6, increase the time, and we store 8 as a discovery and low value of 6. Okay, now from 6 we can go to 7. So this cross edge is there, right? So beginnerly, if you will see, there are 3 kinds of edges. This is a forward direct edge, right? And this is a cross edge, because it's going to some other part of the tree. It's not a tree, but there are 3 types of edges. So this is called cross edge, this is forward edge. So node 7 is already processed, and it is in the stack. So if you will see stack, node is already in the stack, and the stack variable for 7 is also true. So it's already processed, like it's already visited node. So we will just do the same thing. Low of 6 is equal to minimum of low of 6 and discovery of 7. So discovery of 7 is 4 and low of 6, let's look into the top area. Discovery of 7 is 4 and low of 6 is 8. So minimum value on these two is 4, right? So we will update the low of 6 to 4. So let's do that. We updated the low of 6 to 4. Now after this, node 6 is also completely done, right? And we'll do the same thing. We'll check discovery of 6 is equal to low of 6 or not. And we see here discovery of 6 and low of 6 are not exactly same, right? So we'll just leave it and we will move back to 4 again. Now as we move back to 4 again, we see all the children of 4 are processed and 4 is also done, right? So when we move back to 4 from 6, we'll first do the same thing. We'll check, we'll just compare the low values of 4 and 6. So low of 4 is let's look into the array. Low of 4 is 6 and low of 6 is 4. So if we compare with these two values, 4 and 6, the minimum is 4, right? So we will update the low of 4 as to the minimum value of these two, and it will be 4. So updated array will look like this. Now the processing of 4 is complete, and we see discovery and low of value of 4 are not same. So discovery of 4 is 6 and the low value of 4 is 4, which is not same, right? So we will leave it and move forward. So now we finally come back to 1. So from 1 we again do the same thing. We'll just first compare the discovery and low value of 4 and 1. And as we see, the 1 is the parent element we started with, right? So its value is discovery and low value are 1 and the lowest, so there is no change will be happening, and now the processing of 1 will be complete. So as we see, the discovery of 1 equal to low of 1, because both are 1, right? So we will keep popping elements out of the stack until we get 1. So our stack looks something like this. So we'll pop elements out of the stack until we get 1, which is 6 4 7 2 1, right? So we'll just pop all the elements out of the stack. We'll make the variable on stack false for all of them, and we'll just create an SCC using 6 4 7 2 and 1. And as all the nodes are completed, our algorithm is also complete, and we have all our SCC present. So as you can see in this graph, um, 3 8 and 5, they are like single nodes, right? They do not reach anywhere, so they form a individual SCC. But all the other remaining nodes, 1 2 7 4 and 6, like they're forming a loop. So from 7 as well, you can go to any other node. So this was a cross edge, this is not a loop, but from 7 as well you can go like this, right? And if you want to go to 2, you can go to 1 then 2, and if you want to go through these nodes, then you can use this path. Similarly, from any of these nodes, from 1 2 7 6 and 4, from any node you can go to any other node. There is a path available for that. So they all form an SCC, and hence the output of the algorithm. So it's better than Koseraju algorithm, because Koseraju algorithm was taking three um, three um, three trials to find the SCC in a graph. Like it was performing DFS 3 times. It was performing DFS 2 times, and one time it was traversing the graph to transpose it, right? So the Tarjan algorithm is doing it in a single trial. So it's better than Koseraju algorithm, although the overall complexity will be same, because it's the complexity same as DFS, which is big O of V plus E, where V is number of vertices and E is the number of edges present in a graph. Now if we look into the pseudocode, it's doing the same. So if we were first initialize the ID or discovery, whatever you name it, to 0, we initialize our low array to 0, and we put the on stack to false for every vertex, and our stack is initially empty and SCC components are empty. So for Tarjan's algorithm, for all the nodes which are unvisited, we just call the DFS once. So in the DFS, we increase the ID 1 by 1. So here ID we are taking as time. So here ID represents the time, and once whenever the DFS is called, we increase the time and we just store it in the low and IDs. This is basically discovery and IDs are same. So we just store in the low and IDs of the vertex, and we push it on the stack, and we make the on stack value for V true. Now for each neighbor U of V in the graph, if U is unvisited, so if the neighbor of the child, or if the neighbor of the vertex is unvisited, we call the DFS on it again, and after the processing of that node is complete, so after this DFS U is complete, we'll come to this line, right? So we're doing the same thing. We are just comparing with the minimum of low V and low U, and storing the minimum of those two in the low of V, as we have seen in the algorithm diagram, right? After we complete a node and we go move back to parent, we were performing this operation, right? So this line will come into picture after this DFS is complete, right? When the U is completely processed. So after that, we will just compare the low of U and V and restore the minimum of them into the low of V. If the node is not unvisited, we just cover we check the minimum of low of V and the discovery of U, right? So as you see in the dry run again, like if the node was visited already, we just compare the discovery of the visited node and low of the current node, and store the minimum value in the low of the current node. So we're doing the same here. And after so this loop for a V will end. So this loop for node V will end when the processing of V is complete, right? All the children are done, and they came back, and now the processing of V is complete, right? So once all the neighbor of V are processed and V is processed, we'll come out of this loop for V, and we do the same thing. Like if ID and low of V is same, we just create a new SCC. We pop elements out of the stack until we get V, and we collect all those elements and form an SCC using them. So as we saw on the dry run, we just pop everything out of the stack until we get the uh, node V, and we form an SCC using that. So for applications around this, it's also used as the base algorithm for other algorithms as well. So there are algorithms for finding bridge and articulation points in a network or a graphs. Like, so they are basically these algorithms are basically to find the weak points in a network. For example, let's say if a particular let's say there is a network with the routers and everything, and we want to find out if there is a router setup like this. So if that particular router goes down, the whole network will be divided into two if there is a router like that. So it's used for that purposes, like to find the weak points in some connection, or if a edge is going down. So let's say you have multiple cities and they have roads interconnected with each other, right? So let's say if some one road is destroyed somehow, then the people will not be able to travel to that city. Like that city will be, that part of the city will be isolated. So to find those interconnected points and weak points or weak edges, there are algorithms which uses Tarjan algorithm only. So I'll explain them in a separate video. So that's it for this video, and thank you for watching. Please like, share and subscribe.